Bienvenidos a el ciclo de conferencias de Universidades por la Ciencia, organizado por Fundación UNAM y un conjunto de universidades y centros de investigación en México, Estados Unidos, Reino Unido, España, Brasil, y les agradecemos mucho el que nos acompañe. El día de hoy tenemos una conferencia muy especial a cargo del doctor William Phillips. Es realmente un honor tener al doctor Phillips, quien es además una persona muy cercana a nuestro país, a México. Es miembro de la Academia Mexicana de Ciencias, de lo cual estamos muy orgullosos, y ha tenido un número muy grande de estudiantes, de profesores de México trabajando con él, incluyendo grandes amigos como Luis Orozco. El día de hoy la conferencia es sobre un tema muy especial que vamos a comentar en un momento. And Dr. Phillips is a talented, is a unique scientist, distinguished by his creativity and the impact of his studies. He received the Nobel Prize in Physics at a very early age, long time ago, in 1997, for his research and the development of the laser cooling and trapping of atoms. It's an amazing contribution, an amazing development that has a boundless possibilities for atomic physics. And the impact his development has marks one of these unique moments in science before and after a scientific discovery. And developing this method for cooling and trapping of atoms has a lot of challenges, including instrumental ones. And Dr. Phillips was uniquely positioned to do this work. He made his doctoral research in the Massachusetts Institute of Technology, measuring the magnetic moment of a proton in water, which still remains one of these unique experiments in science. Dr. Phillips today will talk about the new measurement, the quantum reform of the metric system. And we will see that this is one of these new developments that is changing everything, and gets together the technology and the science together. Dr. Phillips is very generous with one of the most precious items we have in the universe, and it's time. The research by William has shown that time is one of the fundamental open questions still remaining, and understanding time is one of the great challenges we have. And Dr. Phillips does with the most precious thing, time, sharing with the dearest and loved ones. So we are particularly grateful that today he will share his time, his extremely valuable time, with all of us. Le paso la palabra con mucho gusto a nuestro presidente de Fundación UNAM, el licenciado Dionisio Meade.
Muchas gracias nuevamente al doctor William Phillips por acompañarnos. Para nosotros que esté presente en este consorcio es un motivo de estímulo, un motivo de orgullo y una muestra del potencial que puede tener este vínculo entre universidades cuando agentes de la capacidad, de la preeminencia y de reconocimiento del doctor Phillips nos acompañan en nuestras reuniones. Muchísimas gracias de veras, es un orgullo y yo creo que acrecienta las posibilidades que nosotros hemos concebido de la nueva realidad después de la pandemia. Esta nueva realidad implica el aprovechamiento de las plataformas, implica el vínculo entre académicos, implica el vínculo entre los científicos, e implica sobre todo la posibilidad de que muchos jóvenes accedan al mundo del conocimiento y encuentren en este mundo la posibilidad de realizar sus capacidades profesionales. Gracias de nuevo a todos por acompañarnos. Es motivo de particular orgullo darle la bienvenida al doctor Phillips y agradecerle además que comparta su tiempo, pero que comparta también su afecto por México. Muchos mexicanos se han formado bajo su protección, bajo su tutela científica, y para nosotros eso es un motivo también de reconocimiento, porque hay más y más científicos mexicanos que están encontrando en la ciencia el camino de su desarrollo. Gracias de nuevo, sean todos bienvenidos y listos para escuchar la presentación del doctor William Phillips.
Thank you very much for all of those kind remarks and the kind welcome. It's a pleasure for me to be here with you, and I'm very pleased to be able to tell you about this topic, which I've called a new measure, the quantum reform of the metric system. And as you've heard, I'm from a place called the Joint Quantum Institute, which is joint between the National Institute of Standards and Technology and the University of Maryland. And NIST is the National Metrology Institute of the United States. And there I'm part of the Laser Cooling and Trapping Group, which is led by Gretchen Campbell and also includes Paulette, Trey Porto, Ian Spillman, Ida Tietzinger, and Charles Clark. And this talk is also under the auspices of the International Union of Pure and Applied Physics, which has been one of the strong supporters of the international system of units since its beginning. And as a member of one of its commissions, I am helping to spread the word about the new quantum reform of the international system of units. So, what is the nature of this reform of the international system of units? Well, the metric system, the informal name of the international system of units, came to us as part of the French Revolution. This was perhaps the biggest revolution in measurement that there was. This painting by Delacroix evokes the kind of a revolutionary spirit that changed the way in which the world measured things, as well as many other things as well. And today, my claim is that we are experiencing the biggest revolution in metrology since the French Revolution. And the nature of that revolution is a change in the definition of the base units of the international system of units. 7 units, the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela, are the basis of all other measurements. And the nature of the revolution is that today, every one of those units is defined by fixing a value of a constant of nature. Now, in order to understand how that is even possible, that we can define a unit by fixing the value of a constant of nature, how it's possible to fix a value of a constant of nature, I'd like to, with apologies to the late great Stephen Hawking, to give you my version of a short history of length rather than a short history of time. Since ancient times, the standard of length has been based on the human body. A foot was a foot. A fathom was the distance of the wingspan of one's arms. A cubit was the distance between the elbow and the fingertip. Well, this was extremely convenient and really important to have such measurements because of commerce. In fact, a history written based on the description of one of the early conquistadors, Cortez, indicated that in Mesoamerica, pre-Columbian Mesoamerica, that units of measure were abundant and that people had units of measure for everything. Here in this wonderful mural, we see some units of volume being used in an active marketplace. One of the traditional units of length. The distance between the navel and the ground of a person is very close to our modern definition of a meter. So, as I said, all this was very convenient because you had the standards of measurement with you all the time, but it wasn't very consistent. If you were buying, for example, fabric from a short fabric merchant, then you might get less fabric than you had expected. And so all ancient societies faced this problem of the inconsistency of basing units of length on the human body. And so one approach was to base the unit of length on a particular human body. In the case of the ancient Egyptians, that was the pharaoh. So the length of the pharaoh's forearm became the royal cubit of ancient Egypt, and this was at least consistent, but it was no longer as convenient as using whatever body was at hand. And so the ancient Egyptians did something that was remarkably modern. They made an artifact. They took the length of the pharaoh's arm and they embodied that length into a stone that was the length of the pharaoh's forearm. And this stone became the standard of measurement for ancient Egypt. People doing things like building the pyramids out in the field used secondary standards made out of wood, and they had to recalibrate them every month. And the rule was that the penalty for failing to recalibrate was the death penalty. These people were really serious about metrology, and the result was that they built things extremely well. The baselines of the pyramids are consistent to a fraction of a percent. They're square to 12 arc seconds. They're really extremely well made because of the seriousness of the metrology. Well, this idea of having an artifact, an object that sets the standard of length, is something that was adopted all over the world. In Europe, for example, it was common for such artifacts to be built into the wall of the town square. And here in the city of Regensburg, in the region of Bavaria in Germany, we see one of these standards of length. This is the standard fathom for Regensburg. And as you can see, it's quite a good size fathom. So this might be an exceptionally fine place to buy fabric because you would get a lot of fabric for the measure of a fathom. But the problem was that if you went to one of the surrounding towns in Bavaria, you would have a different standard of length. Well, this was a problem that was deeply annoying and extremely common throughout Europe. And so it was the French revolutionaries who decided that they needed to solve this problem once and for all. And in the revolutionary spirit of universality, the spirit, the motto of the French Revolution was equality, fraternity, liberty. And so in that spirit, they decided that they should have a standard of length that was available to all people. And so they decided to define a new unit of length called the meter. And the meter was to be 1/10,000,000th of the length between the North Pole and the equator on a meridian going through Paris. And so in order to realize this new unit, this new definition of a unit of length, and when I say realize, I mean to bring into reality this unit, they sent out surveyors north and south from Paris to go to Barcelona in the south and to Dunkirk in the north to measure the length of the meridian along that segment, and then they extrapolated for the rest of the quadrant of the Earth to determine what the length of a meter was. They came back from this expedition, which took them several years and was extremely dangerous because there was a war going on. and they reported their results in units of the old standards of measurement that had been in use in Paris at the time. The feeling was that they had brought, not just to France, but to the world, a system of measurement, or at least a unit of length, that would be good for all times, for all people, à tous les temps, à tous les peuples. And in this medal that was cast in order to commemorate this event, you see a sort of mythological creature measuring the earth, which is indeed exactly what they did. They measured the earth. And that measurement was, as I said, brought back to Paris, and they did the same thing that the pharaohs did, that the ancient Egyptians did. They made an artifact because, of course, it wasn't convenient to continually be doing surveying to determine the length of the meter. What they wanted was a standard. And so they made this platinum bar, 1 meter long from end to end, and deposited in the archives of France. And it is known as the meter of the archives, deposited there in the year 1799. So we see that either the Egyptians were being extremely modern, or the French revolutionaries were borrowing a very ancient idea, an artifact that determined the unit of length. Well, excuse me, some few decades later, the entire world agreed to adopt the metric system. And in the famous 1875 Treaty of the Meter, the Convention du Mètre, the countries around the world agreed that they would adopt the meter as their standard of length. And it was also agreed that they would make a new standard of length. This one, a bar that you can see here, made of platinum iridium, where the standard is that the distance between 2 scratches on this bar is 1 meter. This was preferable to the old N standard, because the problem with an N standard is that in order to determine the length, you need to touch the ends. And that, of course, has the disadvantage that it may wear them down. Here, one could use a microscope to look at the scratch and then translate the microscope using a precision screw drive. And this is the way in which meters could be compared and standards of length could be maintained. So this was the standard of length, the international prototype of the meter, kept in a vault in a town outside of Paris. This was the standard of length for the entire world as of 1875. Well, it was made a few years later. That was the standard of length for the entire world. The problem was that almost as soon as they made this new standard of length, people realized that there were better ways of measuring length. The distance between 2 scratches, even when you're using a powerful microscope to look at those scratches, is not a very easy definition to use. Where is the middle of the scratch? It's a scratch, after all. It's not a very well-defined object. What I'm showing here in this picture is a cartoon of a device known as an interferometer. In the 19th century, people discovered that light was a wave. Newton had thought that light was a stream of particles, but in the 19th century, it was discovered that light was a wave. It was discovered that it was a wave of electric and magnetic fields. And because it's a wave, it means that different beams of light can interfere with each other, and they can interfere constructively when the waves line up to make a brighter light, or it can interfere destructively when the waves cancel each other out to make darkness. And this device, known as an interferometer, can do that, and it can measure length. It works like this. Light comes in and bounces off a beam splitter, a half-silvered mirror that reflects some of the light, so that some of the light will come in and be reflected and sent to this mirror, and some of the light will be transmitted and sent to this mirror. Each of these mirrors reflects the light back, and again, some of the light is reflected toward this screen, and some of the light from this mirror is transmitted toward this screen, and those 2 beams of light interfere so that in some places they make a dark spot, and in other places they make a bright region. But here's the point. If this movable mirror is moved 1/4 of a wavelength of light, this means a small fraction of 1/1,000,000th of a meter, then we will change this pattern from being dark to being light. And that makes it easy to measure lengths that are even smaller than that. So it became easy to measure lengths that were smaller, that is, to measure lengths with a precision that was better than a small fraction of 1/1,000,000th of a meter. And that was not something that you could do by looking at a scratch on a bar of metal. And so for a long time, people used the wavelength of light as a kind of de facto standard. It was not the official definition of length, but it was the definition of length that everyone used because you could make measurements using that definition much better than you could using the international prototype of the meter. Finally, in 1960, which was the year that the laser was invented, the meter was redefined. It was redefined to be a certain number of wavelengths of light from a krypton lamp. You put krypton gas in here, you run an electric current through this this gas-containing bulb, and it produces light, an orange light, and the new definition of the meter said that the wavelength of that light was a certain number of meters, and that became the new definition of the meter. But almost as soon as this definition had been made, so that we now had a definition for the meter based on the wavelength of light, it was found that the light coming from this lamp was not perfectly pure, that the light from a laser was far more pure, that the light coming from this lamp was a mixture of colors, whereas the light from a laser was a much more pure single color. And so people started to use devices like this. This is a helium neon laser that produces a red light, and its wavelength is locked to a transition in molecular iodine. So this so-called iodine stabilized helium neon laser became, again, an unofficial standard of length. People started to use this as their de facto standard of length. Again, as in the previous case, it was not officially in legal meters, in SI meters, but it was the length standard that everyone used because you could make such better measurements, much better measurements, using laser light. And so, again, we faced the situation where the meter needed to be redefined because you had a technology, lasers and laser interferometry, that was much better than the old technology of using a krypton lamp and doing interferometry with the light from that krypton lamp. So the obvious choice, if we'd followed the tradition of the past, would have been to redefine the meter in terms of the wavelength of the light coming from an iodine stabilized helium neon laser. Fortunately, the people at the time did not do the obvious thing. They did something far more brilliant, far more beautiful. What they did was to define the speed of light. What does that mean? The new definition of the meter is that the meter is the length of path traveled by light in vacuum during a certain time interval. If you say how far light travels in a certain length of time is the definition of the meter, you have effectively defined the speed of light in the process of defining what you mean by a meter. So when you say that the speed of light is a certain number of meters per second, that's a way of defining what you mean by a meter. This equation, that the wavelength of light times its frequency is equal to the speed of light, is universal. It doesn't matter what the wavelength of light is, this expression is still true. So what it means is that if you measure the frequency of the light, and this is something that by 1983 people had learned how to do, if you can measure the frequency of the light, and if you define what the speed of light is, you immediately know what the wavelength of that light is. So you see the beauty of this? if someone makes a better laser that is more pure, if someone devises new techniques for measuring the frequency of light, and people did both of those things, this expression is still true, and that better laser, that better technique for measuring frequency, can be used to realize the meter without changing the definition. The improvement in the ability to know what a meter is automatically included in this expression. This is the thing that is so beautiful about it. So here is one of the key things to understand about what happened with length. We started with an artifact. The length of a meter was the distance between two scratches on one of these bars. We realized that wasn't so good. We had a better technology, namely interferometry with light coming from a lamp. And so we defined the meter in terms of an atomic property, a quantum property, the wavelength of light coming from a particular atom, in this case, krypton. But then, when that particular atom was not the best atom you could choose, then the final step was to define the length not in terms of a particular atom, but by defining a universal and fundamental constant of nature, namely the speed of light. And the beauty is we will never need to change the definition again. What a beautiful and brilliant definition. What I'm here to tell you about is that just 2 years ago, the international community brought this same beauty to a redefinition of the kilogram, and for that matter, to a redefinition of the ampere, the Kelvin, and the mole. Why was it necessary to do that now, and how was it done? In order to understand that, I'd like to bring you a light history of mass. Here is a picture of a number of standard stones, artifacts that were used as mass standards in ancient Babylonia. These mass standards had the same problem that all other artifact standards have, that they may vary from place to place. Somebody else has a different set of artifact standards. And so the universality of a definition of mass is lacking. What was the definition of mass in Babylonia? You had a different definition of mass in Europe, a different definition of mass in the Americas. The French revolutionaries decided to attack this problem in the same way that they had attacked the problem of length. They would define a new unit of mass, which they called a kilogram, in terms of something universal, the volume of 1 cubic decimeter of water. That is the mass of a volume of water of 1 cubic decimeter, or 1 liter, as we say. This is beautiful because it relied on the meter, this new universal length standard, and it relied on water, something that was readily available to everybody. The trouble was that it wasn't so easy to use. The density of water changes with temperature. There's buoyancy that changes with changes in air pressure and temperature. And so it was very hard to have a consistent definition of mass based on water. And so they did what metrologists have done so many times in history. They made a new artifact. And here is that artifact. I'm holding not the artifact itself, but the box in which it is held. This is the kilogram of the archives. In 1799, this platinum cylinder, made to be as close as possible to the mass of 1 liter of water, was deposited in the archives of France and became the unit of mass for the nation. A few decades later, at the International Treaty of the Meter, the Consortium du Metre, the countries of the world agreed to adopt the kilogram as the universal standard of mass, and they agreed to create a new international prototype of the kilogram, made to be as close as possible to the mass of the kilogram of the archives. And this is a picture of that international prototype of the kilogram, held under 3 jars of glass to keep it clean. This was, until 2 years ago, the artifact standard of mass for the entire world. And it was the last artifact. This is the definition. The kilogram is the unit of mass. It is equal to the mass of the international prototype of the kilogram. A simple definition, but think about this. We are in the 21st century. The unit of mass for the people of the 21st century is an object that was made in the 19th century based on another object that was made in the 18th century. This is a true scandal. Think about it. If someone were to leave a fingerprint on the international prototype of the kilogram, all of us would lose weight. This is an intolerable situation. And while nobody leaves fingerprints on the international prototype of the kilogram, it appears that its mass is changing nevertheless. Here is a plot of the mass of a number of copies of the international prototype of the kilogram. These copies were made at the same time as the international prototype, made to be as identical as they can be to one another and to the international prototype of the kilogram. The IPK, as we say, was chosen because its mass was the closest to the mass of the kilogram of the archives. All the others were a little bit different, and those differences were cataloged and subtracted out, so that at the beginning, when all of these copies were made, we knew what a kilogram was in terms of all these copies. But as time went on, the mass of those other objects changed. Every few decades, these objects would come back to Paris and be compared against the international prototype of the kilogram, and they did not stay constant. Now, when you look at this graph, you see that almost all of those copies of the kilogram are increasing in mass. Now, this makes you think that what's really happening is that the international prototype of the kilogram is losing mass. The trouble is that it cannot. By definition, the international prototype always is exactly 1 kilogram. But of course, that's not what's really happening. But what does the word really even mean in this context when you have defined the unit of mass to be based on an artifact, this piece of metal that is sitting under those bell jars? What can you do? We had to solve this problem. We had to solve this scandalous situation where apparently the very standard of mass itself is something that is changing in time. How did we solve this problem for the meter? We defined the speed of light. We want to use that same beautiful idea for a redefinition of the kilogram. We want to define the value, to fix the value of a constant of nature, a universal constant. What constant do we use? Well, to understand that, I want to ask you to recall what is probably the most famous equation in all of history, that the energy, E, of an object at rest is equal to its mass, m, times the speed of light squared. E equals mc squared, almost certainly the most famous equation in history. We have another equation for a different kind of energy. This is Planck's equation. The energy of a photon, well, he didn't use that term, but we now call a particle of light a photon. Its energy is equal to Planck's constant times the frequency of the light. Remember, light is a wave. It has a frequency at which the electric and magnetic fields wave back and forth. That frequency times Planck's constant is equal to the energy. Now, what I'm going to do is take those two equations and set them equal to each other, because they are both equations for the energy, and solve the mass. So the result is that the mass is equal to Planck's constant times the frequency divided by the square of the speed of light. What does this mean? If you had an object, a particle, let's say a nucleus, and the nucleus radiates a photon, a gamma ray. So we might imagine any number of radioactive nuclei that give off gamma rays. The change in mass of the nucleus after it gives off a gamma ray that has a frequency f is equal to Planck's constant h divided by the square of the speed of light. Now, this isn't the way we're going to do our new mass measurements. We're not going to weigh photons. In principle, we could. In fact, we do weigh photons, but not well enough to serve as a mass standard. This is where this wonderful genius Brian Kibble comes in. What Kibble said was, let's imagine an electromechanical device. We now know it as a Kibble balance or a Watt balance. And let's use it along with a definition of Planck's constant to define the kilogram. So here's how it works. In this movie, I'm going to illustrate how the Kibble balance works. So first, I'd like you to remember how we measure mass traditionally. When we want to measure an unknown mass on this side of a balance, the way we measure it is we put known masses on the other side of the balance, and we keep putting masses on the other side of the balance, known masses, until the balance balances. And when it balances, then we know that the unknown mass is equal to the sum of these known masses. This is the traditional way of weighing things. Now I want you to imagine a different way of weighing things, one that uses electromagnetism. So imagine that on the other side of the balance from the unknown mass, which produces a gravitational force, we have a device that can produce an electromagnetic force. This device has a coil of wire in which we're going to put current. It has some magnets that create a magnetic field. And here's the current going through this coil. Here's the magnetic field. And the point is, if we know what this current is, if we know where the current goes in all the wires of this coil, if we know the strength of this magnetic field, and we know the direction in which that magnetic point, the magnetic field points at each one of these wires, then we can calculate what the electromagnetic force is. We then will know, once it balances, that it's equal to the gravitational force, and by knowing the acceleration of gravity, we can determine what the mass is. The problem is this: we do not know any of these things well enough. We don't know where the current goes in this coil. We don't know what the magnetic field is or what direction it's pointing in. And so while we can imagine this way of doing things, we can't really use it as a way of measuring mass, as a different way of measuring mass. Here's where Kibble comes in. He says, yes, we can't measure these things, but we can measure something else. What Kibble said was, take this coil that we're putting current through, and take the leads of that coil, and don't put current through, but connect those leads to a voltmeter. Now, let's move this coil up and down and measure its velocity. We call this the velocity mode of the experiment. We're going to move it and measure its velocity. And when it moves, it's going to generate a voltage. And so we see that when we move this coil at a velocity that we're going to measure very carefully, it generates a voltage, and we're going to measure that voltage very carefully. And what Kibble understood, and I'm going to show you how it works out in just a moment, he understood that if you made this measurement, all those things that you didn't know about the magnetic field and the direction in which it points and where the current goes in the wire, all of those things would be incorporated into this measurement of the voltage and the velocity. And then you could use this new idea, as it turned out, to measure mass. So let's see how that works. And that different way is the one that involves the Josephson effect. Here's Brian Josephson, and the quantum Hall effect, discovered by Klaus von Klitzing, and here's von Klitzing. What Josephson told us was that if you have two superconducting materials and you put them close to each other with an insulating layer between and put a voltage across them, there will be a current flowing at a certain frequency. And the frequency divided by the voltage will be given by this fundamental constant of nature, 2e over h, where the 2 comes from the fact that in superconductors, the electrons are paired and work together. So E over h, the charge of the electron, Planck's constant. Here's where Planck's constant is coming in, you see. What von Klitzing discovered was that if you have a certain two-dimensional semiconductor and you put current in one direction, it'll generate a voltage in the other direction, and the ratio of that voltage to the current has the unit of ohms, and the value of that resistance is quantized in units of h over e squared, h being Planck's constant, the thing we're trying to get, and e, of course, being the charge on the electron. And so, when you measure the voltage, you do it using Josephson effect, and then the voltage is proportional to h over 2e. When you measure the current, you do it by putting it, the current through a resistor calibrated using the von Klitzing effect, so the resistance is in terms of h over e squared, and then you measure the voltage across that resistance, which again is measured in units of h over 2e, and you see that the h's cancel out of this current measurement, so the current's proportional to E. You multiply that times V, which is proportional to h over 2E, and it's proportional to h. So that's how we get mass proportional to h. So using this idea, people around the world, including my colleagues at NIST, have made devices that do this. Here's a picture of one of the devices at NIST that does it. And with this device, we can realize the kilogram. That is, we can determine the mass of an object in absolute kilograms to a part in 10 to the 8th, and that is better than the changes that we're seeing happen to the kilogram due to, well, we don't really know what those changes are due to. Because we don't have a solid standard of mass, something that we know doesn't change, but now we do. And so I'm just calling it dirt, but maybe in the future we'll figure out what it is now that we have a way of determining mass, a way that doesn't change because it's not based on an artifact. And so we're working on it. And what the future of time will be, I can't predict, because we're still working on what is the best new atom to redefine time. And so we come to the end of the talk, but it's not really the end because we still need to redefine the second. Thank you very much.
Muchas gracias. Thanks very much. It's great listening to you. And congratulations for your studies and research. It's very interesting. And thanks for sharing your enthusiasm and passion for science. The last comments illustrate how science works, how scientific questions are being put forward, and how you need to move on, and what made the new discoveries. I think it's great hearing how you consider science. And I was also thinking about one of the questions and the importance of having this new system and having these high precisions. And this is, of course, particularly important for science and scientific experiments, but it is also important for our everyday life. When the laser was developed, I think nobody knew what the applications will be and what the importance. We have the laser everywhere in the supermarket. It's our best way to measure distances and so on. So these new discoveries at this incredible precision we now have in the future, and perhaps in the very near future, will represent our new technological, our new tools. So thanks very much, and we also very much appreciate your friendship and generosity particularly for our students and young researchers. Muchas gracias. Felicitamos al doctor William Phillips felicitamos al doctor William Phillips por la conferencia y por su trabajo de investigación y por la generosidad y la amistad. Y la parte que hace interesante su trabajo es pues la pasión, el entusiasmo que se le pone. Y esto yo creo que es pues la clave del éxito. Y cuando uno hace algo con el gusto de hacerlo, yo creo que cuando salen mejor las cosas. El doctor Phillips es miembro de la academia y participa en muchas de nuestras conferencias y actividades con los estudiantes, con los profesores, con la colaboración de proyectos. Entonces realmente es muy importante. Le agradecemos mucho entonces al doctor Phillips, agradecemos al Consorcio de Universidades por la Ciencia. Reiteramos pues que este ciclo de conferencias es parte de esta colaboración internacional muy amplia con universidades en el país, en Estados Unidos, en Inglaterra, en España, Brasil. Es una de las prioridades de Fundación UNAM en adición a los numerosos programas de becas. Le voy a pasar la palabra a nuestro presidente de Fundación UNAM, el licenciado Dionisio Meade. Thanks very much, Araxi. Thanks, Demetrio. Thanks, everyone. And I will invite our president of the UNAM Foundation, Dionisio Meade, to say a few words. Thanks very much again.
Thank you very much. It was a pleasure. And I just want to make a small comment. It's very, particularly William Phillips, he has the particularity to explain in a very easy way very complex problems. But it was very easy to follow the talk. And I have a number of comments of some students and colleagues, and they have the same impression. It was an incredible talk. And very easy to follow. As I said, explain these ideas in a very easy way is a very difficult task. And well, thank you very much for the conference. It was my pleasure.
A pleasure for me as well.
Muchas gracias de nuevo. Ha sido pues una gran conferencia. Hemos aprendido mucho, sobre todo los que no somos expertos en ciencias. El metro ya no es lo que era, el litro ya no es lo que era, un kilo ya no es lo que era, y nos ubica pues, en el formidable mundo de la ciencia que hoy se nos presenta nuevamente. El tiempo y el espacio que hoy nos han permitido a cada uno estar presentes en esta plática sigue siendo para cada quien un gran misterio. Pero es un misterio al que nuestros jóvenes están convocados a sumarse, a investigar, si se suman a este mundo de la ciencia, a este mundo de la investigación que William nos ha descrito de manera fascinante. ¿Por qué vale la pena entrar a este mundo? La nueva realidad es una búsqueda permanente del conocimiento y la nueva realidad demanda, como aquí se ha visto, el respeto a la ciencia, que hoy es un imperativo. La conferencia del doctor Phillips acredita el avance de la ciencia que se da día a día, aún en temas que parecían ya resueltos. Por eso hay que estar abiertos al conocimiento. Ojalá esta plática de William Phillips convoque a nuestros jóvenes a entrar en este fascinante mundo, a este mundo fascinante de valores y de conocimiento. El doctor Phillips también tuvo un día, su primer día de clases. El doctor Phillips un día también hizo su primera investigación. Y con ese trabajo duro, un día recibió ese telefonazo a las 3 de la mañana que acreditó que se había ganado el premio Nobel. Gracias por compartir esa experiencia. Gracias por suscitar esta inquietud de preguntar, de ser como niños. Ese deseo de saber lo llevó al premio Nobel. Quizá entre nuestros escuchas haya alguien que en el futuro pueda obtener también un premio Nobel. No estoy seguro de que nada le daría más gusto al doctor Phillips que a alguno de los que estén escuchándolos, siguiendo esta sed de investigación, esta curiosidad de saber, se genere también la obtención de un premio Nobel. Gracias por compartir y gracias por sembrar estas semillas de concordia, de compartir y de competir. Ahí está la esencia del saber. Ese es el propósito de nuestra universidad. Ese es el propósito del consorcio y es lo que ha animado a seguir adelante en este esfuerzo. Gracias a todos. Ha sido una gran presentación y seguimos contando con usted en el futuro, que seguimos contando que seguirá formando a muchos científicos mexicanos y que el mundo se verá beneficiado de esta posibilidad de más y mejor conocimiento. Gracias a todos y seguimos con entusiasmo estas pláticas que el consorcio nos ofrece martes a martes.
So, but it has been a true pleasure to be with you, and I thank you for all of your comments and your questions. It's been a wonderful experience. Thank you very much.
Fundación UNAM cumple 30 años de sumar apoyos por las y los estudiantes de la máxima casa de estudios. Desde sus inicios en 1993, su propósito ha sido fortalecer ámbitos de la vida universitaria como la docencia, la investigación y la difusión cultural. Hoy cumplimos 30 años becando a jóvenes universitarios para que continúen su vida académica a través del mayor proyecto por la educación superior. Cumplimos 30 años alimentando su garra, con apoyo nutricional para no abandonar sus estudios. 30 años de llevar tratamientos de salud comunitaria con el profesionalismo humanitario de los alumnos a zonas rurales. Pasamos 30 años otorgando becas de movilidad para que las y los estudiantes accedan a una educación sin fronteras. Además, en uno de los momentos más difíciles para la humanidad, protegimos a médicos residentes y enfermeros universitarios que luchaban en la primera línea de atención ante la COVID-19. Premiamos la investigación científica para promover el desarrollo del conocimiento universitario y abrimos espacios de reflexión para fomentar la divulgación de la ciencia, el arte, las humanidades, las sociales y muchas más. Gracias por formar parte de Fundación UNAM. Nada de esto sería posible sin tu apoyo, porque contigo hacemos posible lo imposible.